Okay, good afternoon, everybody. So if you can hear me, can you please put it on the chat? Put it on the chat that you can hear me, please, so I'll go on with the teaching. If you can hear me, let me see it on the chat. Tell me you can hear me on the chat. Okay, thank you so much. So we have to start the class now. I've already shared my screen, and as you can see, starting with a recap of our class on Monday. The recap is going to take the question and answer format. So I have some questions here, and I believe by the time we finish answering all the questions from A to E, we should be able to understand better what we said the last class about using quantum numbers to describe an electron in an orbital and all of that. So the question says, can we please again have our hands on our chat box, because you will be giving me the answers either on the Q&A platform, that's the question and answer platform, or the chat box. The question says, which of the following cannot exist? Which of the following do you think, based on the quantum number that describes this, that this particular orbital cannot exist in the form that is described here? Now let's go with the A. A says if our N is equal to 4, our L is equal to 4, ML is equal to -2, and MS is equal to half. What do you think about A? Can this exist or not? So I'll go to the chart to look at your answers. A cannot exist. Can I have other answers? A cannot exist. It's just few people that are answering me, please. No, we are still looking at A. Let's take it one at a time, because we need to explain why do you think, if you say A cannot exist, why do you think A cannot exist? Give me the reason why you say that A cannot exist. Yes, the answer is that A cannot exist. Good, but why? What's the reason? Because L equals to N minus 1? Good. Because L equals to N minus 1. And so our N is 4. 4 minus 1 is not 4. So because we have here L is equal to 4, this particular orbital cannot exist with this quantum number. I mean, this particular electron cannot exist in this orbital with this quantum number describing it. Our L cannot be equal to 4 since N is equal to 4. So let's look at B quickly. We have to finish what we have for today. B says N equal to 3. I hope those of you that are listening on the YouTube, you have your biro and you have a paper you're writing on. Because these things, let me tell you one thing about practicing in class. You might think that you're wasting your time, but no. When you write it down in class, you should be able to identify where your mistake is. And when you go back and look at it, you will not make that mistake again. So don't just assume that we are wasting our time. We are not wasting our time, because these things, they are volatile. If you don't get it right now, if you don't get it very well, I don't know. Let me not say anything, but let's just move on. B says N equal to 3, L equal to 2, ML equal to 1, MS equal to 1. What do you think about about B. Can B exist? I'm coming back to the chart. Good. Omokaro, it cannot exist. Please, what is your reason? B cannot exist. Correct. B cannot exist. Can you give me your reason or your reason, please? We've not gone to D. All these people that are flying to C and D. When I give you one now, you will say, you don't know it. Please, let's take it one step at a time. Oluwabusola, why are you going to M equal to 5? What do you mean M equal to 5? Can you please let me understand so I will address what you have written, because what you have written is in no way related to what we are saying. We do not have 5 here, so how are you coming up with 5? So B cannot exist because MS will take a value of what? Plus half or minus half. That is spin up electron or spin down electron. So MS cannot be equal to 1. So A cannot exist because L cannot be equal to 4 when N is equal to 4. Then B cannot exist because MS cannot be equal to 1. Now let's go to C. Can C exist? Fast. Please, we have to be faster. All these people are writing attendance. Answer my question first. Can C exist? Adika Chioma, I want you to say C can exist, because if you say yes, ma, I don't know the one that you're saying yes, ma, to. Can C exist? If I don't get up to 50 answers, I won't go to the next question. Give me your answers. All these people are writing their names on the platform. So it's your name that is more important than listening to the class and be part of the class. Write your name, no wahala. C can exist, good. I'm counting. If I get 50 answers, we go on to the next one and we look at why C can exist. Okay, actually C can exist. Then let's go to D. Can D exist? First one. Can D exist? Just few answers for D, we'll move on. Can D exist? Can D exist? Yes. I have some answers here. Correct answers. I just want one person that will give a negative answer so that I will know how to go about the next topic I want to look at. That's the reason why I brought this recap in form of activity in class. It's going to enable me know the level at which you are following the class. But it seems all of you are just getting the answer, which I'm not comfortable with anyway. It's a good one, but I'm not comfortable with it. Okay, I have a Conway frame promise. Or you just want to tease me because I said somebody must get a negative answer. Ah, these children. Okay, let's go to E. We'll come to the reasons why all of this cannot or will exist. Let's go to E. Will E exist? This one, anybody that fails it, a knock on the head. We are on E now. E. We are on E. We are on E. Asade Temitayo. Oko, who promise? You just wrote that in for me to be happy, yeah? Because I said somebody must have a negative answer. Why did you not get E? Can E exist? Good. Someone has already given us the reason. Now, some people are saying they don't understand. I don't know if these people are in my class yesterday, because someone telling me that he or she does not understand. Maybe you have to meet me personally. I don't know where you don't understand, because this is just a part of what we did yesterday. So if you don't understand this part, that means that you don't understand from the beginning. That's just what it means. You can't tell me it's just a part of the whole thing. Quantum numbers is just a part of the whole class. So let's go on to see the reason why we say A cannot exist. Now, for A, if we want to write out A to describe the electron that exists in that energy level, the energy level is equals to 4, L equal to 4, ML equal to -2, MS equals to +½ We said that this cannot exist because if our N is equals to 4, our L is going to be what? N -1, which is 3. So our L will start from 3. Are we together? Our L is going to start from what? From 3. Our L is in the 3rd energy level. So, not 3rd energy level. Our L is 3. So L is what? 0 is S orbital. P is 1. G is what? D is 2. And F is what? 3. So it's a subshell of an F orbital. L, it should be a subshell of an F orbital, which is 3, and not L equal to 4. Now, the second number B says N equal to 3, L equal to 2, ML equal to 1, MS equals to 1. Why this cannot exist is because MS is equal to 1. MS can either be -½ or +½ So we have L equal to 2, telling us that we have what? It is a D what? Subshell. If L equal to 2 is a D subshell. And if ML equal to 1, and you have MS is equal to 1, which is wrong. It is wrong. So you have this as 3D, but because it's wrong, we are not going to go further to write the number, this thing that is there. So let's go to number C. Number C is correct because our L is 3. Our L is 3. And if our L is 3, that means that we have what do they call it? The subshell that we have is 3. Now, remember that for your subshell, the ML is equals to -L to what? To +L. So if -L to +L, so you're going to take -3 to what? To your +3. This is actually in the F orbital. And in the F orbital, the 0 there is going to take one of the F orbitals that are there. So ML is equals to 0. It is correct. Remember that for that 3, you still have the whole of what do they call it? The whole of -3 to +3. Now for G, N is equals to 1, L is equals to 0. Here you're actually saying that you have what? 1s. So number C is telling you that you have 4D because your N is equals to 4. That is your energy level. If L equals to 3, that means D. So you have 4D. So remember that you have how many degenerate D orbitals? You have about 5 degenerate D orbitals. So you need to look at the one that has that particular the one that that is accommodating the electron in it. Now let's go to the last one. The last one is very simple because there is no energy level of 0. So there is no need to look at any other thing there. So it cannot exist. N starts from 1. So this one, N is equals to 0, so it cannot exist. Now, in summary or a recap of what we had done on Monday, we are saying that you use 3 quantum numbers to describe an orbital. 3 quantum numbers will describe an orbital. Those are the principal quantum number, the azimuthal quantum number, and the magnetic quantum number. While 4 quantum numbers will describe an electron in an orbital. Please, these are 2 different things. 3 quantum numbers will describe an orbital. 4 quantum numbers will describe an electron in an orbital. So do not mix it up. And those 4 quantum numbers are principal quantum numbers, the mutual, magnetic, and what? And the spin quantum numbers. Those are the 4 quantum numbers that can describe an electron in an orbital. So here you have 4D, here you have 3, 013P, then and all of that. Now we've been talking about the orbitals, S, P, and all of that. Want to look at the assigning an electronic configuration to this orbital. How do you assign electronic configuration to these orbitals? Now, electrons are assigned based on the energy level. But even as that, it follows a certain rule. Those are the rules that we are going to look at today. And there's one important thing about the electronic configuration. The electronic configuration helps us in understanding the bonding ability of properties of an atom, their magnetic property, and other chemical properties. Now, there is something I want us to note here. When we talk about the electronic configuration, giving us a better understanding of bonding ability and all of that, when we are looking at the property of an atom, we are actually considering the valence electrons, because it's the valence electrons that actually confines a property to a particular atom. So we are not going to be looking at, yes, the whole configuration, it's okay for understanding, but when we want to confine or when we want to look at the properties of that particular atom, what we consider is the valence electron. The valence electron is what we call the outermost electrons. Now, because we have said that in assigning electrons to an orbital, it has to follow a general rule. Now, one of those rules is what we call the Aval principle. The Aval principle is actually the principle of building up. What it means is that the atomic orbitals are filled with electrons from the lowest to the highest energy. The atomic orbitals are filled with electrons from the lowest to the highest or the greatest energy. Now, there is a scheme here that shows the increase in the energy level, in the energy of the orbital. Now, you start from the 1s orbital, when the 1s orbital is filled with electrons, and like we said on Monday, that each of these orbitals will accommodate a maximum of 2 electrons. And also recall that there are some orbitals that have degenerate orbitals. For example, the p orbital has 3 degenerate orbitals, the d orbital has 5, the f orbital has 7, and so on and so forth. So each of these orbitals will accommodate maximum of 2 electrons before you move to the next energy orbital or to the next higher energy orbital. Now and again, on Monday, we say that for the degenerate orbitals, that, okay, that's the next rule. Let me not go into that. We'll see it in the next rule. So after filling the 1s, we go to the 2s. After filling the 2s, we go to the 2p. After filling the 2p, the 3s, the 3p, the 4s, and the 3g. Now, if you look at what is happening, one might say, why is it that, look at, we are supposed to fill the 3d before the 4s? Listen to me. These electrons are filled in the orbital based on the energy. The orbital that has the lowest energy will be filled first before the orbital that has the higher energy. Now, the 4s orbital at the ground state has a lower energy than the 3d orbital. So electrons are accommodated in the 4s orbital before moving to the 3d orbitals. Now listen to me again, just for knowledge sake. But for Fsc111, what I'm going to say now, you don't need it. But in your second year, when you'll be taking up your CHM211 class, you need to understand this. Now, once this is what we have written, once electron drops into the d orbital, remember you're going to fill this 4s orbital to have 4s2 before you go to the 3d orbital. Now, once you put in one electron in this 3d orbital, the energy of the 3d orbital becomes lower again than the 4s. And as such, in removing electrons, remember that electrons are being removed from the orbitals that have the lower energy. When you're removing electrons, the reason why electrons are being removed from the 4s orbital before the 3d orbital, electrons are filled in the 3d. Once electron enters the 3d orbital, the energy drops lower than the 4s. So the 4s becomes higher in energy than the 3d once electrons are filled here. But when you start the filling of the electron, listen to me. You fill 1s will have 2 electrons. You fill 2s, the 2s will have 2 electrons. The 3p orbitals will have 6 electrons, 2 each. The 3s orbital will have 2 electrons. Now, the 3p orbital will have 6 electrons, 2 each. The 4s orbital will have 2 electrons. You fill the 4s orbital. Now, once you put 1 electron in the 3d and you have 3d1, the energy of the 3d becomes lower than the 4s. And so, this 4s will now come here, and that is why when you want to remove electron, you remove electron from the 4s orbital before removing electron from the 3d. This is also the case when you come to 4p and 5s and 5d orbital. Let's go on anyway. That is for your knowledge. Now, there is also the Medlog way of looking at this building up electron. This is just following the arrow. 1s is filled, comes 2s. After 2s is 2p and 3s. After 3s is 3p and 4s. You see? Then after 4s, you have 3d, 4p, 5s, and so on and so forth. So the first rule is that you must obey the Aufbau principle. Electrons will go into the orbital with the lowest energy before going into the orbital with the highest energy in this order that is presented here. Now, the second rule is the Hund's rule. All of us know that. We've been hammering on this, so I'm not going to waste time. It says that for the degenerate set of orbitals, that what you do is, first of all, you fill the electrons singly before occurrence will occur, before pairing the electrons. For example, we have this particular electronic configuration here to my left, which I said that it is incorrect because one of the p orbitals have 2 electrons in it, while the others are empty. This electronic configuration is wrong because it did not follow the Hund's rule. But the second, going towards my right, you could see that this particular electronic configuration obeyed the Hund's rule. Electrons in the p orbitals are filled singly. So instead of filling it the 2 electrons on one orbital, it is filled singly here. So each of these orbitals has 1 electron each. Also, you could see that in nitrogen, each of the p orbital in nitrogen has 1 electron. So the next atom is oxygen. So the extra 1 electron in the oxygen will start now going inside, going into the p orbitals to cause, to pair each of the single electrons that are here. Now we have another rule. The third rule is what we call the Pauli exclusion principle. The Pauli exclusion principle. This principle is just telling us that no 2 electrons in an atom will have an identical set of 4 quantum numbers. And it is only the ms that will separate these orbitals, because if I write n equal to 3, L equal to 2, I'm coming. If I write n, okay, let's start with, I want to write, as you're writing, me sure I'm writing. If I say n equal to 2, L equal to 0, and M equal to 0, what I am saying is this, that I have 2s orbital, isn't it? 2 is my n, L equal to 0 is showing that it is s orbital. Now, if I have n equal to 2, L equal to 1, and I have ML equal to, then ML is going to be from -1, 0, plus 1. The reason is this. I am saying that if my N is equal to 2 and my L is equal to 1, that it is a 2p orbital. And if it's a 2p orbital, I have 3 degenerate 2p orbitals, which are 2px, 2py, and 2pz. That is -1, 0, and +1. And remember, electron can decide to enter into any of these degenerate orbitals. It does not matter if it goes first into the pz or py. They are of the same energy level. So the only thing now that will differentiate this electron is when I have their spin, either up or down. If their spin is up, it's going to have a spin number of +½ And if it is down, it's going to have a spin number of -½ So that is what will differentiate them. And so that is why you do not have 2 electrons in an atom. Like, this is not correct. This is not correct at all. Even if I have filled all of these 2 and I have this spin up together, it is wrong, because one has to spin down to differentiate electrons and all of that. Now, paired electrons will have opposite speed. So, but this one disobeyed how many rules? I'm going to the chart box. It's not only the Pauli exclusion principle rule that it disobeyed another rule. This particular electronic configuration by my left here. Can you tell me another rule that this particular electronic configuration disobeyed? Let's go to the chart. It is two rules. What are they? Write them out. The Hund's rule and the Pauli exclusion principle. Somebody said the Aufbau principle. Is that correct? Okay, let's go because of time. Now, the person that said is the Aufbau principle, you are wrong, because remember that for the Aufbau principle or law or rule, is just telling us that we need to do what? We need to accommodate electrons in orbitals, starting from the orbitals of the lowest energy to the orbitals of higher energy. In this case, this particular electronic configuration obeyed it, because it started filling with 1s, which is of a lower energy, going to 2s, which is higher than 1s, and going to 2p, which is higher than 2s. But it did not obey the Hund's rule. The Hund's rule says that when you have the degenerate set of orbitals, that each orbital will accommodate one electron each before you start pairing. This one starts pairing immediately here, and these ones are empty. It disobeyed that. Again, it disobeyed the Pauli exclusion principle rule or principle, because the Pauli exclusion principle says that no 2 electrons in an atom have identical set of 4 quantum numbers. And I told you that for this to happen, it means that an orbital can hold a maximum of 2 electrons, and those 2 electrons must be in opposite spins. That is what it means. It must be in opposite spins. That is pairing on. You have to pair electrons for them to have opposite spins. But this disobeyed it because this is spin up, this is spin up. They are not opposite. So this is wrong. If you look at the one of 2s, it is correct because this is spin up, this is spin down. This is spin up, this is spin down. But when you come to the 2p, both of them are spin up. The electrons are spin up. So this disobeyed 2 rules. Why this is correct. Now let's go on to look at some electronic configuration of some of the 20 elements that we have. Now I brought this out so that I will show us that this is what we call the orbital diagram. That is when you put them in the orbital. It might not be in a box sometimes. It might just be dashed. The way you have it in this previous slide is still orbital diagram. Am I communicating? Now, this other way is still what we call the notation. So this is the notation of the electronic configuration notation, and this is the orbital diagram. It's still the same thing. It's just for you to understand it in case if you want to follow anyone. But I can tell you that before even you put your orbital diagram, you must have written down your notation somewhere. So let's start with hydrogen, which is the first element in our periodic table. Hydrogen has 1 electron accommodated in the s orbital. Then the next element is helium, or the next atom. Helium has 2 electrons accommodated in the s orbital. Now, because we said that each orbital will accommodate maximum of 2 electrons. After helium, the next atom will have electrons in the next orbital of higher energy, which is our 2s. So electron will start dropping to 2s, and 2s again will take maximum of 2 electrons. You could see that this helium here and this one here is still the same. So you can also write your electronic configuration in a condensed formula. So instead of writing lithium as 1s2, 2s1, you can put your helium in parentheses and now put the valence electron 2s1. So for that condensed electronic configuration, writing up of electronic configuration, the way it goes is that the core electrons, that is the core electrons, are written in parentheses with the valence electron written outside. And remember, when we talk about valence electron, we are talking about electrons that are accommodated in that energy level. For example, if I have 2 as my n, that is 2 as my energy level. 2 has 2 orbitals, the 2s and the 2p. So it is both 2s and 2p that are called valence electron. It is not only the 2p, please. It is both 2s and 2p that are valence electrons. Now that is being explained in boron. In boron, you have 1s2, 2s2, and 2p1. And so, if I want to write this in a condensed way, I will write my helium in parentheses. Then I will now write, Then I will now write 2s2, 2p1. So my valence electrons are 2s2 and 2p1. So boron has 3 valence electrons. Some of you always say that boron has 1 valence electron. No, boron has 3 valence electrons. And now I want you to put it in your notes or whatever you're using your jotter. We'll look at all these valence electrons, and when we'll be doing our class on Friday, which is when we'll be looking at a brief discussion on periodic tables, you will see that each of these elements or atoms are being classified in a group based on the number of valence electrons they have. So just be noting down the valence electrons. We have boron having 3 valence electrons. Let's see if we have boron in group 3 or whatever. I don't know, but when we get to that, when we get to the next class, we should be able to note that. So that's how you write your electronic configuration all through to the first 20 elements. I was able to bring out the first 20 elements of the in the periodic table. So these are their electronic configurations. So what you're going to do now is to look at, write them in a condensed formula. In writing them in a condensed formula, you're making use of what? You're making use of the core electrons. Let's look at magnesium, because some of you will misunderstand me. Let's look at the electronic configuration for magnesium. If you look at the electronic configuration for magnesium, everything is paired, isn't it? It has electronic configuration 1s to 3s. This is not a core, it cannot serve as core electrons, because this 3s still has available, this third energy level still have available 3p and 3d orbitals for bonding. So you cannot write magnesium in brackets and now say that the valence electron for aluminum is 3p1. No. There are available 3p and 3d orbitals that you can use for your bonding. But let's look at the elements that are core, that have core electrons. If you look at helium, helium is 1s. After the 1s, it has 2 electrons, and that is all. You're going to go into the next energy level. So there is no 1sp. So this is core. So let's look at neon again. Neon, all the p orbitals are paired. So you're going to go transit into the next energy level, which is 3. So helium, neon, argon are the 3 core, are the 3 elements that have core electrons in them. Calcium again has the 4s electron field, but these electrons are not core because there are available 4p, 4d, and 4f orbitals that you can use for your bonding. So electrons can decide to move from here during excitation to the next available higher orbital. So those ones are not core electrons. So that's why I tried to bring it out here. You have oxygen. Oxygen is 1s2, 2s2, and 2p4. The core electron we have here is this. So you have your valence electron as 2s and 2p. 2s and 2p. So oxygen has 6 valence electrons. Let's look at sodium. Sodium has a core electron of what? Of neon. 1s2, 2s2, 2p6 is neon. If you look at it, is neon. So the next energy level is 3. So that will not be our what? Our valence electron. So you have neon 3s1. So this is how to write it in abbreviation and all of that. So I want you to understand what valence electrons are and what your core electrons are. So in writing your electronic configuration, you can decide to use any one that you want. If you want to write it through this notation, fine and good. If you want to use abbreviation by recognizing the core electrons in the parentheses and now writing the valence electron, it is fine. But please do not assume that because an orbital is filled up with 2 electrons, that has made that a core electron. No. In case of calcium and magnesium that we have seen. Now, remember that we said here that, let's go back, that when we know the electronic configuration of a species, it will help us in understanding better the bonding ability, the magnetic properties, and other chemical properties. The bonding ability we are going to look at when we go further, maybe in our maybe in other courses. But as far as this particular course is concerned, I've told you that for your bonding, you use the valence electrons. They are the ones available for bonding. And that is why when you look at one group of electrons, you look at group 1, you say that group 1 electron, they are known for this particular chemical reaction. It's because in group 1 electrons, all of them, they have 1 electron in their as valence electrons. So that is what confines that unique property to them. When you move to group 2, you say that they have this particular property, or these ones are metals, these ones are non-metals, and all of that. It is because of the valence electron that they possess that has given them that opportunity to have a similar or one kind of reaction in them. We want to look at magnetic property, which will just look at the electronic configuration and decide whether such will be magnetic or not. So when we talk about magnetism, we are going to look at two types of magnetism, the paramagnetism and the dimagnetism. So we'll say that an atom is paramagnetic if that atom has an unpaired electron in it. And if an atom is paramagnetic, it means that that atoms will be attracted to a magnet, because it's, there is something here that is like empty. Let me just put it like that in a layman's language. But when the electrons are paired in an atom, that particular electron is said to be diamagnetic, and diamagnetic atoms are repelled by a magnet. Now let's go back to some of this electronic configuration we have here. If you look at this oxygen is diamagnetic. Excuse me. Oxygen is diamagnetic because you have unpaired electrons in this orbital. In the p orbital, there are presence of unpaired electrons. So we say that oxygen is a paramagnetic atom. Sodium again is a paramagnetic atom because you have 3s1. 3s1 is unpaired, and so because of the presence of this unpaired electron, it makes this sodium to be diamagnetic. This is another example here where you have, this is still oxygen electronic configuration, where you have this and this unpaired. The two p orbitals, they have unpaired electron in them, while here you have all the electrons paired. And so this is a diamagnetic atom. Whatever atom that has this electronic configuration is diamagnetic in nature and will be repelled by a magnet. So whatever atom that has this particular electronic configuration is paramagnetic and will be attracted to a magnet. Now again, we are going to have our hands on this particular question. What do we have next? The question says, what is the electronic configuration and orbital diagram for a sulfur atom? And what are the 4 quantum numbers? The electronic configuration of sulfur. First of all, you should know the atomic number of sulfur. Then you write the electronic configuration. The atomic number of sulfur is 16. I think you should just put down the question and try to like attempt it. So I have to go to my, the next screen too has, it has the answer to the question. So no problem, just, I know it's not going to be easy writing this because you don't have a way of doing the subscript. But once you write 1s2, I will understand. So can you give me the answer right now? I'm on the chat box. I'm not seeing anything. The electronic configuration of sulfur. Somebody is asking, can we start the arrangement with a down spin? There is no rule that says you should start with any spin, but it's better to start with your spin up, just for simplicity. But there is no fast and hard rule that says start with this particular spin, up or down. But usually, over the years, or by default, it's been with a down spin. So why don't you go on with that? Sulfur is not 3p6. Somebody says 3s2, 3p6. Oluwabusola, are you sure? Okay, you can do the subscript. That's good. Okay, it was a mistake. Good, because I know you'll be following the class. So can you give me the correct answer now? I'm waiting for you, Busola. No. Are you in error? 3S1, you said 3S1, and you said 3S2. I guess it's a mistake. Can you correct yourself now? Boluwa, can you correct yourself? Can it be written in which way? Somebody is asking me if it can be written in this. I can't see what you wrote to answer your question. Yes, it can. Good, you can. That means yes, you can. That is correct. Good. Good, that is correct. No, this person has actually brought out the different types, the different degenerate p orbitals, px, 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 2px, 2py, 2pz, and assigned electrons to them and brought out the 3p's. You're correct, I give it to you. Kudos, it can be written very well. That is the best format to write it to show that you understand what you're doing well. Thank you so much. All these meta math students that are giving me their matric number, I just remove you from my destiny. Better answer my question instead of giving me your matric number. You can come and sit down. Somebody is telling me something is filled before we start pairing. No, the 3s orbital. S orbital is not degenerate. Please. S orbital is not degenerate. So S orbital has to be fully filled before you go to P. It is P, D, and F orbitals that are degenerate orbitals. So for S orbital, anytime you're filling any S orbital of any energy level, whether it's 10s, the S orbital has to accommodate 2 orbitals first. The 2 orbitals has to be fully taken before you start going to the next higher energy level, please. Did you understand that? I want to get the person that wrote that. Someone asked that question. Good. Some of you now are using the abbreviation method, giving me neon 3s2 and 3p2 correct. So let's quickly go to the next question. He says we should also give the orbital diagram. This I know is very difficult to give here, but please try and do it. Try and write the orbital diagram and make sure that you separate the degenerate p orbitals. Don't put them together, please. Separate them, let them be on the same energy level because they are degenerate. Now, what are the 4 quantum numbers? What are the 4 quantum numbers? So I'm going to go here. I'm going to move to the next slide so that I'll look at your chart. What are the 4 quantum numbers for sulfur? Give me my answers. There is no time. What are the 4? How can we write the abbreviation? We can write the abbreviation of it in the electronic configuration. It is neon in bracket 3s2, then 3p4. That is the abbreviation format. You take the core electrons in parentheses, then the valence electrons, you write them out. I don't think I can answer you Technospark 7 because you don't have a name. Technospark 7 is telling me that he or she does not understand. And Technospark 7 is no name. Techno is not a chemistry student. Techno is not a University of Lagos student. So please, when you are logging in, log in with your name so that we'll know whom you ask. If you have any question, we can address it. Okay, somebody asked, I think L is equal to 1, Abi. Why is a we'll address that, get to that. Somebody has no time. Let's go and answer the question. Now, let's look at what we have. We have the 4 quantum numbers that will describe the sulfur is n equal to 3. If n is equal to 3, L equal to what? Okay. I understand this question, but somebody has answered that question correctly on the chart. Somebody answered that question correctly on the chart, and I want to note the person. We are going to take this question, we are going to take the answer together. There is something I deliberately did now. Now, this question can come in 2 ways. I've asked you what are the 4 quantum numbers if n is equal to 3. I can ask you what are the 4 quantum numbers for the valence electron. For the valence electron, you know, you're actually looking at 3s2 and 3p4. Good. Now, if n is equal to 3, L is equal to what? Can you give me what L is? Remember that when we started, we said that L will go from 0, 1 to n minus 1. Listen to me. Can you stop writing and listen? Somebody has gotten the answer again. L is 0, 1, 2, but let me explain now. If you go to your last slide, the slide of the last class, we say that L is dependent on N. True or false? Answer me quickly. Let me go on. Chat. L is dependent on N. Are we together? Yes or no? L is dependent. Good. And ML is dependent on, answer me. ML is dependent on dash. ML is dependent. Good. ML is dependent on L. Now, you see this answer, you bring the answer yourself now. L is dependent on M. ML is dependent on N. Now, when we say N equal to 3, we're actually saying that our L is equal to 0, 1, 2, 2, N minus 1. Are we together? So if N is equal to 3, that means that our L is equal to 0, 1, and 3 minus 1 is what? 2. Are we together? 3 minus 1 is 2. So our L is equal to 0, 1, and 2. That is what our L is when N is equal to 3. Because L is dependent on N. So if we say that N is equal to 3, our L is going to be from 0, 1, 2 till N minus 1. That means that our L is 0, 1, N minus 1 is 2. So you have 0, 1, and 2. Now listen again. Because we have L 0 to 2, N is 3. The third energy level will have 3 orbitals. 3s, 3p, and 3d. But if you look at sulfur, do we have electron in 3d? Answer me quickly, yes or no? Do we have electron in 3d? Do we have electron in 3d? Do we have electron in 3d? Good. There is no electron in 3d. So for us, for sulfur, L equal to 2 is wrong. There won't be any L equal to 2 because L equal to 2 shows that it's a d orbital. L equal to 2 shows that it's a d orbital. No, L equal to 2 shows that it's a d orbital. We have electrons in the S and P. Somebody said electrons are only in the S. No, for sulfur, electrons are in the S and in the P. Just look at the chart. I mean, the slide that I'm sharing. L is S and P, but our L is 0. Our L is 0, 1, and 2. But because there is no 3D, electrons are not in the 3D. Cancel that 2. 2 is not part of what we are going to look at. So we are going to be looking at 0 and 1. And 0 is S, 1 is P. It's not only 1. No. Whoever that says it to be 1 is wrong. It's not only 1 because the valence electrons are both in the S, 3s, and 3p orbitals. So here, if n is equals to 3, our L is going to be 0 and 1. 0 and 1 is 3s and 3p. It's going to be 0 and 1, 3s and 3p. So this one that I wrote here, L is equals to 1. Now I remember that I did put it. Does it mean that we have 4 orbitals in sulfur? I don't understand what you mean when if we have 4 orbitals in sulfur. The orbitals we have in sulfur are here. We have 1s, 2s, 2p, 3s, and 3p. There is 3d because the third energy level will have an empty 3d. But because of the electrons in sulfur, there is no more electron to go to d. So it will just be there, waiting for anything, any excitation or whatever that will cause it for the electrons to move to a d orbital. We have 4 values of magnetic quantum numbers. We have 4 values of magnetic quantum numbers. What this means is this. We have 0 and we have 1. Then ml for 0, because ml goes from minus L, 0, and plus L, isn't it? You're going to be taking it one after the other. For your 0 here, ml is 0. For your minus 1, ml is minus 1, 0, and plus 1. And that is why you have under ml is equals to 0, you have 0, 1 orbital. Under ml is equals to minus 1, you have 1, 2, 3 plus 1, 4. And that is why you have 1, 2, 3, 4. 4 orbitals that is here in the outermost shell. 1 of the 3s and 1, 2, 3 of the 4 of the 3p, making it 4. They are all coming from your ml. So let me give you, I think the next one explain it better. Don't worry, you will get it. You don't need to wait to bother yourself at all. This is what we are saying. This is what we are saying. If I want to describe the valence electrons in sulfur, I told you that these 2 questions are the same because when you're asked to write the 4 quantum numbers that describes an atom, I've told you that the important thing for us in any atom is the valence electron, because that is what confines property. I mean, that is what brings about the property of that particular atom. So that is our interest. Now, and the 3p, please, these other core electrons, keep them out of your sight for now. Just pretend as if you don't see them. Focus on the valence electron, which is the 3s and the 3p orbital. And remember that these orbitals, now they have electrons in them. So you will be describing the electrons each. We say that 4 quantum numbers describes one, it will describe an electron, which is the N, the L, the ML, and the MS. So I want to start describing these electrons. Now I start with the 3s. I'll take the first electron here. Remember, 3s has 2 electrons. I'll take the first one. I want to define it. That first one, my N is equals to 3. My L is going to be 0 because it is at s orbital. I know that L is going to be 0 and what? 1, because I have N is equals to 3. So my L is going to be 0, 1, and 2. But because I don't have, what do they call it? Okay, we've said that we don't have electron in the D. Let's just forget about that now. So I have 0, 1, and 2. And this is 3s. Which one represents S? It is 0, isn't it? So I'm going to put 0 under L. This is my 0. And if my L is equal to 0, my ML automatically is going to be 0. Then I'll have my spin plus half. This is half, not 12, please. Plus half. I've defined one of these electrons. I have 2 electrons, so I still have another electron in the 3s. I'll take up that one electron in the 3s. I want to define it again. The N is 3. The L is 0 because this is 3s. The ML is 0 because S is spherical. It is not dimensional. MS is minus half because this one is spin down, minus half. This one is spin off, plus half. That is why you have plus half here and minus half. Now I finished with describing the 4 quantum numbers for the 3s. I will now go to the 3p. Again, the 3p, I have one of the orbitals having 2 electrons. I'm taking the electrons one after the other because what I am describing is quantum numbers for each of the valence electrons. They didn't tell me quantum number for just one electron in each orbital. So I'll take it again. Here, there are 2 electrons in this p orbital. I assume that this my p orbital is px. So I'll say 3px. I'm going to define my 3px now. For my 3px, my n is going to be 3. My L is going to be 1 because it's a p orbital. My ML is going to be minus 1. Remember that ML is from minus 1 to what? It's going to be from minus 1 to plus 1 because your L is what? 1. Then my spin is going to be spin up, which is plus half. That is my 3px. Now, for my 3px, the second electron, the only difference will be in their spin. Which of the rules describes this? Which of the rules? Hello, which of the rules? The Pauli exclusion principle, remember? It says that no 2 electrons will have the same quantum numbers. And I told you that the only way there will be difference is in their ms. That is the spin quantum number. So that is why you're having minus half here. Everything will be the same except this, because these 2, they are the same orbital, but different electrons. When I'm done with the 2px, I'll go to the next one, which is my 2py. My 2py has just 1 electron. So I'm just describing 1 electron. 3, 1, plus 1, and plus half, because the spin is up. I'm done with that. Then I'm going to the 3pz. The 3pz has 1 electron again. I'm going to describe it. 3, L is equal to 1. This one, L is equals to 0. Why is L is equals to 0? Because ML runs from minus 1, plus 1, and 0. It is 3. So I've taken care of minus 1 here for this px, plus 1 for my py, and the other one will now be 0. Because the electron spins off, it's going to be plus half. And that is my 3pz. Here I've described the valence electrons, each of them one after the other. If you look at what is happening here, if we bring out the common thing here, for our n, it is 3. For our L is 0 and 1. And that is why in this question, and I told you that here, it's going to be 0 and 1 because you have 3s and 3p. Then let's go to the third one, which is ML. Our ML, we have 0, 0, minus 1, plus 1, and 0. So it's going to be minus 1, 0, and plus 1. Because we cannot be putting 0, 0. We are just bringing out the like terms. That's why I say, let us bring out the like terms. I'm using sulfur here. I use sulfur the last one. The reason why I use this is for you to understand it better. Now let's go to the last one, which is our MS. Let us bring out the common factors here. The common factor here is just plus half and minus half. So if I come back to this question and I say that, I asked you what are the 4 quantum numbers to describe my sulfur. The 4 quantum numbers would be n equal to 3, L equal to 0 and 1, ML equal to -1, 0 and +1, MS is equal to +half or -half. I have done that, and that is the same as bringing them out one by one. It's a summary, because here you take a common factor, which is 3. Here you take common factor 0 and 1. Here you take common factor 0, -1, and +1. You understand? So that is how it goes. I don't know what I have on the chart. What is a typo error? Somebody said typo error. I want to know what is a typo error so that I'll know how to address it. Yes, we label 0, 1, 2 as S, P, and G. For L, if your L is equal to 0, 1, 2, they stand for S subshell, P subshell, and D subshell. If your L is equal to 0, 1, 2, and 3, they stand for S subshell, P subshell, D subshell, and the 3 will stand for what? F subshell. That is how to label them. Correctly, you're correct. That is how to label them. So that when you have 3S, you will not know where the number that it will assume. Because it's S, will you assume 1 or will you assume 0? Are we together? So for my 3PY, ML is meant to be 0. For your 3PY, ML is if you have given a 3PZ your 0. Why is PZ 0 and not +1? It's still the same thing Victor is asking that you're asking. For L is equals to 1, what is your ML? Again, Victor and this other guy, you be the one to answer me now. You'll be the one to answer me now. Is half, not, as I've said, it is a typo error. Is +half and -half, please. I said it. Choma, I said it is a typo error. You think your 3PY is 0, ma? It depends. It depends on what I do. It depends on what you take. I don't want to go deep into it. Any of the P's, they are degenerates. The only thing is that you must assign your ML to the 3 of them. And if L is equals to 1, which you have understood, you understand that one, that your L is equals to 1. Your ML is what? Your ML is -1, 0, and +1, isn't it? Now, if you look at this particular one, we have given our -1 to PX. We are left with 0 and +1. No problem. If you say 0 here, you will say +1 here. There is no hard and fast rule about that. The only thing is that the 3 degenerate p orbitals must take this ML -1 to 0. That's all. So depending on what you're taking as your internuclear axis, which I don't want to go into here, that will tell you what your 0 will be or +1. But for now, just know that for the 3 degenerate orbitals, your ML is equals to 1. I mean, your L is equals to 1. That means ML is equals to -1. Numbers, share it for them. You can give your PX 0. You can give, because for now, I don't want to tell us what we'll be using as internuclear axis. I don't want to confuse us in that. Let us understand the assignments that we are giving first of all before we are nuclear axis or not. So if you understand what I've said now, that will be all. I wanted to go into shielding effect, but we'll start it on Friday. On Friday, please, we are finishing on Friday. These children, eh? Okay, take the PZ as internuclear axis? The ML part. The ML is dependent on the L. The ML is dependent on the L. So if you understand L, if L is 1, don't crack your brain on the ML. If L is 1, ML is -1 to 1. And you know that in between -1 and 1, there is 0. So it's going to be -1, 0, and +1. If your L is 2, your ML is going to be -2 to 2. So it's going to be -2, -1, 0, +1, +2. If your L is 3, your ML should be from -3 to 3, which is -3, -2, -1, 0, +1, +2, +3. So there is nothing to like, you're not trying to do any arithmetic here. Just note what your L is. Your ML is dependent on your L from -L through 0 to +L. So that is what you should note. Yes, because they're on the same energy level. There is what we call internuclear axis. Those points, you know, when we look at the P and the D degenerate orbitals, you see that we have Cartesian points that we drew that says XYZ. Now, if you look at the XYZ, it depends on the internuclear axis. That is where the arrow is going. Is it going towards X, towards Z? And you know that most times your Y is in between. I guess that's why everybody, they are just saying that Y should be 0. No problems about that, so far as you understand. But what I did was for you to just know how to assign your ML to your degenerate orbitals when they have electrons. So because these p orbitals, they are degenerate. So you have px, py, and pz. Even when you're reading your alphabet, it's xyz. You understand? For simplicity, it's xyz. So when you're drawing, you could see that sometimes z will come before the others, but usually your y runs in between. So you always have your x and your z as internuclear axis. And so they should assume the position of either +1 or -1. But no problem about that, so far as you understand one. Just change it in your own notes. And before I give you the slide, I'm going to change it. But what I want you to understand is that we just assigned -1, 0, and +1 to our degenerate p orbitals. It's just like if I have this, if I come here now, I will say that this is my -1, this is my 0, this is my +1. It's because this is px, py, and pz. I guess that's why you are saying it that way. But it's fine by me. I am happy that at least you're following what I am saying. So that is what we mean when we say ML. For here, our ML is 0 because L here is 0. So I think that will be all for today. I have question and answer. Let me look at if there is any question. Ma, how will you know if MS is to be +half or -half? Now, when we say +half, we are actually talking about a spin that is up. A spin up is assigned +half, and a spin down is assigned -half. Usually when you're feeling, you always feel the arrow up before the down one, isn't it? So the arrow up, when it's up, usually signify that as +half. And when the spin is down, we say it is -half. That is your anti-clockwise. That is minus. So that is what just it means. That's what that sign means. So it's not as if you know by it is you. If you want to start your spinning, but that's not convenient enough, by the arrow down. There is no fast and hard rule. Nobody says, there is no rule that tells you that when you want to assign or draw your electrons, that you must start with an arrow up or down. No. But for convenience sake, it's usually very easy and simpler to start with the arrow up. And that is your spin up. And that is +half. If you start with this one down, it is your -half because it is anti, and this is maybe, it has an anti of the other one. bonding and anti-bonding and all of that. That is the answer to that question. If you don't understand anything, then you have to meet me because my time is up, and I guess you may have another class now. Do I have anything on the chat? Nothing. So thank you all. We meet on Friday. Please try and read. I'm going to send this. I'm going to send this thing now. I'm going to send your slide while I correct this one to your coordinator so that you will read ahead on Friday. On Friday, we'll still come back to this just briefly because periodic table, I guess, is not going to give us hard time. It's something you know. So we look at quantum numbers again for you to understand it better, and do have a good afternoon. Thank you so much. Bye for now. Oh, my office. My office. These children. My office is foundation building. So my name is Dr. Joy Keze. When you come to foundation building, the second floor, the third row, as you're entering 1, 2, 3, the third one, just look for my name. That is my office. Now, if I'm not in the office, kindly write a note, put your number, put it under my jaw. When I come back, I'm going to tell you that I am going to call you back that I am around, because I get to do some other administrative work, like looking at the brush sheets and all of that. I'm a course advisor. So, but once I see your notes and your phone number is there, be rest assured I'm going to give you a call when I'm seated, and you come and look at whatever you have. Thank you so much and have a nice day.